Good morning and welcome to this Conservation Applied Research and Development or CARD webinar, which will address the question of whether nanofluids are ready for prime time. Thanks for joining us today. I'd like to cover a few housekeeping items before we start. All attendees will be in listen-only mode. We will answer all questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send them to all panelists. The Q&A box can be opened by clicking the ellipsis in the lower right of your screen, as indicated on this slide. We'll do our best to answer all questions within the time allocated, but if we don't get to some for some reason, we will answer them after the webinar. This webinar is being recorded and will be available on the department website in a few weeks. The slide set from the webinar will also be available on the website, but if you need it sooner, email me directly. Finally, if you would like closed captions on this webinar, click the CC bubble in the lower left of your screen. I'm Mary Sue Lobenstein, and I'm the Research Planning Director at the Minnesota Department of Commerce, Division of Energy Resources. In that role, I identify and analyze gaps within utility conservation improvement programs and coordinate and plan research to fill those gaps. The CARD program is a major tool of that work. With me today is Adam Zoet, an Energy Planning Director at the Department of Commerce, where he specializes in the regulation of electric and gas utility energy efficiency programs. He is the project manager of the research that is the subject of the webinar today, and he will moderate the Q&A portion of the presentation. Our presenters today are Joe Corneo and Bryce Dvorak, both from Michaels Energy. Joe is an assistant energy engineering manager at Michaels Energy, where he performs energy analyses for custom rebates, energy audits, and investment grade studies. These efforts including detailed data analysis, field investigations, and data logging. Joe is the primary investigator on the study that's being presented today. As Director of Operations at Michaels Energy, Bryce provides operations oversight and leadership, budget and resource management, product development, and client satisfaction. In his previous role, he oversaw all efficiency program implementation staff and work at Michaels Energy. Welcome to you both. We look forward to your presentation. To provide some context, this webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal. About $2.6 million is set aside annually for the CARD program, which awards grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their Conservation Improvement Program or CIP portfolios. As you can see by the pie chart that's here, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is one of those that crosses multiple sectors, and we'll discuss results from a recent CARD project that investigated the potential for energy savings and cost effectiveness from replacing standard heat transfer fluid with a nanofluid medium. Now I'll turn it over to Joe for today's presentation.
Thank you, Mary Sue. Good morning, everyone, and thank you for joining us for this presentation today. So in terms of the agenda for the presentation, it'll show us the roadmap of what we're going to include. First, I'll start the presentation by going into the background of nanofluids and the theory behind them. Next, I'll explain our procedure for conducting this study, and then as we proceed through the description of the study, I'll show the results of our data analysis. And then finally at the end, we'll present some lessons learned, some conclusions, and recommendations. So first, to give some background on the technology we'll be talking about today, it involves the use of suspended solids in conventional fluids like water or glycol to improve their thermal conduction behavior. It's an old concept that spans into the previous 19th century, but until relatively recently, there have been disadvantages to installing suspended particles technology into fluids with micro or macro particles. And these disadvantages have to do with the particles settling rapidly and reducing the heat transfer benefits, and then also the erosion of equipment that can happen with the larger particles. But recent technology has allowed for the development of nanofluids, which involves the suspension of the nanoparticles, which are less than 100 nanometers, to be suspended within conventional fluids. And these can remain suspended in the fluid without settling. So again, this study aims to evaluate the potential of these nanofluids with energy efficiency. In particular, there's a commercially available product called HYDROMX, or HYDROMX, that is the basis of this study that we evaluated. The existing, a note on some existing research surrounding the heat transfer of this particular nanofluid. This diagram here shows an experiment at the Heating and Cooling Laboratory in the Republic of Turkey, where they conducted some experiments to determine the performance of the HYDROMX nanofluid. The experiment depicted by this diagram involved the addition of a steady amount of heat into a closed loop on the right-hand side of this diagram, and the heat exchanger located towards the upper or middle portion of the diagram, and the heat transfer rates to the left-hand side of the heat exchanger were analyzed and compared using 100% water and then a 50-50 mix between water and HYDROMX, and the fluid flow rate on the right-hand side was kept constant. And this study concluded that the capacity for heat transfer through the heat exchanger was approximately 8% greater when using the HYDROMX solution compared to just water alone. However, the study did not quantify the energy impacts or implications of this nanofluid on heating or cooling systems. There are a series of case studies that are out there, and this table summarizes the available research that we had as part of this study. Some of these examples, case studies, contain methodology that are based on sub-meter data, while others involve billing data. The methodologies vary, but each of these studies fall a little short, in our view, in a similar way. From our best assessment, none of these studies accounted for differing weather effects on the system, and we feel that the data should be normalized for these effects. Additionally, most of the results reporting that we saw as qualitative and without detailed engineering backup. The results were only mostly available in PDF format, so we weren't able to independently verify or reverse engineer any of the results from the raw data or information. This technology is out in the field currently. These are two examples of projects that have been rebated in the state of Minnesota. They both involve the replacement of glycol with HYDROMX. We at Michaels have reviewed the methodology and data for both of these analyses, and we deem them reasonable and accurate using our best engineering judgment and available information at the time of the analysis. The project on the left-hand side involved the fluid replacement in a chiller, and then on the right-hand side was the fluid in a heat recovery loop. As you can see, the chiller measure had a longer payback at about 12 years. compared to the heat recovery loop. That was about less than a year. Those differences stem from a couple different factors. The first was that the loop volume and the cost requiring to fill the system was much smaller in the heat recovery case than the chiller. Additionally, the savings benefit was able to be realized in the heat recovery loop throughout the year, whereas chillers only operate during the summer. So in terms of our study, this graphic shows the total number of test sites that we included in it. Our goal at the onset was to have at least one chiller, one condensing boiler, one non-condensing boiler, and also to make sure we had a boiler in a residence. We were able to include additional equipment and systems where it made sense to do so, resulting in our study included a commercial water-cooled chiller, a commercial air-cooled chiller, both commercial condensing and non-condensing boilers, and then both a residential condensing and non-condensing boiler. In terms of the process of the study, we first took measurements and then the baseline case, and then observed the fluid replacement process with the HYDROMX nanofluid. The process varied slightly between among each site, but they all comprise the key basic steps, and that you had to make sure that you noted the pressure of the loop before replacement, before you drain the fluid. When you did drain the system, you wanted to make sure that all relief valves were open and either hoses connected or allowing the pure water to drain naturally. Using a transfer pump, you'd mix the pure HYDROMX fluid to get the right concentration you wanted with tap water to ensure the right mixture, and then you'd fill the system with the transfer pump and close it, making sure you had all the valves closed except the very highest point, and make sure that you had it pressurized to the same level that you had when you started. This table summarizes the results of our study, which we'll go into in subsequent slides. But the key takeaway from this slide is that the data showed positive energy savings at some sites, while others had limited or negative energy savings results. This slide showed some of the differences in our methodology between commercial and residential sites. Our primary goal was to develop a system efficiency across the system's operating range that accounts for applicable weather effects, since the previous studies didn't necessarily show that. So these efficiencies are in the form of kW per ton for chiller systems and therms of natural gas per MMBTU for boiler systems. Specifically for the commercial systems, we looked at it on a system basis, so that energy input into that system was compared to the HVAC system's heat transfer to determine the operating efficiency we used. We downloaded data at regular intervals or obtained automation data from the facility owners as it was available. We did add metering points to existing automation systems where necessary. And since standard heat transfer equations don't apply to this technology, according to the manufacturer, we developed alternative analysis approaches. And then for the residential systems, we looked at it on a whole building level, under the assumption that there's less variability in the system operation and the loads. And then so the utility bills served as the energy input in that case. So our first site involved a water-cooled chiller. at a municipal office building. This particular system served a series of several small air handlers. We replaced the fluid in the chilled water loop, or the evaporator side of the system, and we installed a flow meter on the condenser water loop, and then this data point was used in conjunction with other automation data points to estimate the cooling load on the chiller. The analysis involved normalizing the results based on outside air temperature, and we created an efficiency curve plotting the impacts of the nanofluid installation against outdoor air temperature to determine the efficiency gain of the system across a range of operating conditions. In terms of the data quality for this site, we did have full automation access to this site in real time, but the one thing that was lacking was a true power measurement on the chiller, and we weren't able to take a measurement of the power factor on the motor due to some difficulty in accessing the panel. So these charts show the outdoor air temperature displayed along the horizontal axis, which is can be thought of as a proxy for the cooling load. The chiller efficiency in kW per ton is on the y-axis. On the left-hand chart, the orange line is the nanofluid period in 2021 cooling system. As you can see, it's higher than the blue line in 2020. The calculated chiller efficiencies that you see are much different than what the chiller is rated for, which is about 0.82 full load kW per ton rating versus in the range of anywhere between 1.2 and 1.5 kW per ton based on the data. On the right-hand chart, the main takeaway there is that the decrease in cooling efficiency varies by outdoor air temperature, but without much of a real correlation to any weather conditions. So, as seen in the table here, the energy savings were estimated to be negative in this case. And we feel that a major contributing factor is that the data indicate that chiller loads were about just 1/4 of the equivalent full load hours that are stated for chillers in the Minnesota TRM, and even the data indicate that the chiller was only about 50% loaded during the warmest outdoor air condition period in the baseline in particular, and we also found that the chiller had or appeared to have a chilled water reset sequence that kind of further decreased the load at many conditions. A note on the fluid quality, this photo highlights a foaming issue that we found on site. On the left-hand side is an optimal fluid, the optimal fluid condition that was taken from our air-cooled chiller site, and the right-hand sample shows foaming where air wasn't able to be properly purged from the system. And this foaming, as confirmed by the manufacturer, really inhibits heat transfer, and some steps were made to mitigate this. However, the issue hasn't been completely resolved even to this late date. Therefore, due to some of these, both the loading and this foaming issue, we're not sure as to whether we can really trust the data that came out of this site. The second site is the air-cooled chiller, and it's at the same municipal office building in a different wing of the complex. But This chiller served a single air handler, and our methodology for estimating the efficiency involved calculating the cooling load directly on the air handler using, again, the automation data points. We then compared this to the power input to the chiller to estimate the efficiency. And since we had full BAS building automation access for this site, including true power KW results, we're more confident in the results from this site. Additionally, just the nature of this chiller serving a single air handler required us to make fewer assumptions about how the system operated. These are some similar graphs to in design to the previous site. The left-hand graph shows a general trend that could be more to be what expected. With the blue line efficiency being higher than the orange line. So this, in both cases, it shows that the system's less efficient at higher loads when it's warmer outside. The chiller's cooling capacity is about 100 tons at full load with a rated efficiency of about 1.2 kW per ton. The meter data shows the chiller efficiency closer to 1.4, but the low loading on the chiller is likely the primary cause of this issue. On the right hand graph's trend shows a more significant efficiency increase at lower outdoor air temperatures and loads than in the peak loading conditions. Okay, as seen from this table, our data analysis resulted in positive energy savings in this case, and consistent with the gain in efficiency shown on the previous graphs. As mentioned, the calculated loading was relatively low in a similar fashion to the water-cooled chiller. So, if you were to apply the load from the equivalent full load hour loads from the Minnesota Technical Reference Manual, you'd get about 4 times the energy savings than shown on this slide. The third site is a non-condensing boiler. This system serves a single air handler that has heating coils in the zones. We also had full automation access for this site, and we pulled the data intermittently before it was overridden. This setup included a gas meter that we were able to data log, as well as airflow monitoring through each of the terminal heating coils. So we calculated an air side load at for each of the coils, and then compared that to the natural gas input to estimate the efficiency. Our data analysis involved a linear regression of the gain in efficiency based on outdoor air temperature as a proxy for weather data. And then this regression was applied to the baseline weather data to get a gain. The left-hand graph here shows a higher efficiency in most cases in the nanofluid period, with the orange line being higher than the blue line. It also shows that the boilers peak at about 50% efficiency, which is much lower than would be expected. And we were told by personnel familiar with the system that some radiant heating panels that were tied to the system were no longer active, and we assumed that this was accurate. However, based on these these calculated efficiencies, and as well as some indications from some subtle clues from the automation system, we have reason to believe that these heating panels were active for at least a portion of our monitoring period. The chart on the right shows a scattershot of points, but the intent here is to show that the gain in calculated thermal efficiency after the nanofluid installation is most significant at mild outdoor air conditions when the heating loads are the lightest. So the results of our analysis showed that we gained positive energy savings based on our analysis. However, the incompleteness of the data and the loading, capturing the loading, makes it hard to draw confident conclusions from this site. Again, the building loads that from the data indicate are far lower than we'd expected. The typical boiler loading based on the Minnesota Technical Reference Manual is about 12 times that of what we calculated at peak heating conditions in our analysis. Again, this ties back to at least in part due to some additional heating loads that weren't captured in our analysis likely from those radiant heating panels. The fourth site involved a series of condensing hot water boilers at a rehabilitation facility. This system serves not only some HVAC coils, some heating coils, but also a series of subloops that serve a pool heating system, general domestic hot water, as well as a snow melt system. So it's the primary hot water loop feeds all of these subloops via a series of heat exchangers. Our fluid replacement process for this site involved replacing glycol in only 2 of the subloops, one of them that served air handler coils and another one that served the snow melt system, since these were the only closed loops available. The main heating loop remained unchanged in the pre and post with water, only due to our approach and how we wanted to estimate the load on the system. If we were to change the fluid in the main loop, it would compromise our loading calculation. We didn't have full access to the automation system at this site, and we relied on a third party to pull data from the system. So, this was done in some separate batches for each heating system. And the 2020-2021 heating season was our baseline period, and then the 2021-22 this past year's heating season represented the nanofluid period. And our analysis for this site involved normalizing the results only by supply water temperature. On the graph at the right, the baseline line is blue, and that's higher than the nanofluid line in red. So it kind of shows that there's negative energy savings here. In terms of the total load calculated in the nanofluid, we applied those loads to the average efficiency of 96% in the baseline. As you can see, it's kind of a relatively flat performance there based on hot water temperature, and that determined the energy savings, which, as you can see, are negative in this case. We didn't attempt to normalize the operation of this system to a typical weather year because the demands on this, or the loads served by this boiler, were not a typical space heating boiler. We do feel that we received some reasonable data quality and had to make limited assumptions. However, there were some changes in apparent operating sequences that makes us less confident in the results for multiple reasons. As you can see, the boiler efficiency on the chart at the right does increase with higher temperatures in the nanofluid case, which isn't the typical performance for condensing boilers. And also there's not really a good explanation for the dip in efficiencies as shown in the red line. The average estimated efficiency across the operating range in the nanofluid case is approximately 87%, which is less than we expected. And lastly, as shown by the lines on the chart, the boiler operated at higher supply water temperatures in the proposed case by operating at different water temperatures that can affect the performance of the boiler as well. The fifth site is a condensing boiler at a single-family residence. This boiler served 2 air handler coils, and as shown in the chart at the right, the data indicate that there is some small positive savings. Again, the site had a much simpler metering plan compared to the commercial sites, so and we're pretty confident that there wasn't a major change in operating schedules at this residence, since it housed a retired couple across the whole metering period. Our analysis methodology for this site shown in the graphs. The left-hand graph shows the amount of therms consumption per month compared to weather data in the form of heating degree days. We created regression lines to approximate the performance both in the pre-data and post-data periods. As you can see, these regression lines are nearly on top of each other, so we assume that there's a minimal energy impact from the nanofluid installation. The graph on the right shows a time series of energy use. We modeled the baseline, which was water. So on the gray side, we're comparing this modeled baseline with the actual baseline, the actual bills, which in theory should always be close. And then after a break for the nanofluid installation, we get to the green side where we compared our modeled baseline with the billed consumption. And then the difference between those two green lines in the chart shows the cumulative energy savings across that whole period, which is represented in the dotted line. Our sixth and final site is a non-condensing boiler in a multifamily residence. It serves hot water, baseboard radiation in a fourplex. And the energy savings summary at the right shows negative gas savings. We have a little bit less confidence in these results just due to the higher potential variability in the occupant schedules, with it being a fourplex. Though the occupants didn't indicate as such through a customer survey, their daily schedules may have been impacted by the stay-at-home orders in 2020. As with Site 5, the left-hand graph shows the therm consumptions per month compared to the weather data. The green line, which represents the baseline data, is consistently lower than the gray line, regression line, meaning that this is a constant negative in terms of savings. And then the time series energy use graph on the right, again, similar to Site 5, we modeled the baseline with water. On the gray side, we're comparing the modeled baseline with the actual baseline, and then on the green side, we're comparing the modeled baseline with the build consumption. And the dotted line shows the cumulative negative savings impact. In terms of issues that we did encounter and lessons learned as a result of this study, the following unforeseen issues were encountered and led to some lessons learned. First, the monitoring of the commercial sites was carried out from starting in about February of 2020 to May of 2021, just between the heating and cooling systems. And this obviously coincided directly with the reduction in occupancy levels in commercial buildings in response to COVID-19. And this lack of building occupancy caused low loading and kind of across the board in the equipment and systems we observed. The varying levels of data access inhibited our ability to do some troubleshooting of data in real time, and that led to some data quality issues. The varying types of data available through the building automation systems also skewed results to a degree. And again, going back to the example of the difference in how we calculated chiller power input between the water-cooled and the air-cooled chiller. And then finally, it proved difficult to find sites that were willing to pilot the technology. Our project team spent over 5 times the amount initially budgeted for recruiting on this project, and we needed to request an extension of the project timeline. We encourage future study providers to consider the challenges that are associated with recruiting participants that are willing to test out emerging technologies. In our final assessment of the study, we feel that the results are ultimately inconclusive, and we can't substantiate the permanence of energy savings resulting from this nanofluid installation across the board. Therefore, we don't recommend that this technology be included in any prescriptive programs at this time. However, that's not to say that the technology does not save energy definitively. We do see energy savings potential and recommend that projects be eligible for incentives as part of a custom rebate or grant program that based on detailed site-specific data monitoring, similar to the 2 projects I described earlier in this presentation. In terms of further study, at this juncture, we recommend it's preferable to put this nanofluid in a laboratory setting in a controlled environment to validate the energy savings potential of this technology. Thank you.
Great. Thanks for that great presentation. If you have not already done so, please type any additional questions into the Q&A panel and send them to us. Adam, do you have any questions for Joe or Bryce?
Yeah, I've got a couple. One question would be, can you provide the details of how costs were estimated for this measure?
Yeah, sure thing, Adam. Yeah, and the way we used it, we approximated costs, taking figures from the HYDROMX manufacturer, and the specific figures for this study used $67 per gallon in cost. So those costs varied based on the different loop volumes. There are some rules of thumb for both heating and cooling systems in terms of loop volumes, based on what's your cooling capacity of your chilled water plant, say. You could expect 3 to 6 gallons per cooling ton. However, even those results those are rules of thumb, so the actual requirements can vary widely and even vary by a substantial amount between our different heating and cooling sites.
Great, thank you. And another question from the audience is, how easy is it to uninstall a nanofluid installation? Do the nanoparticles persist in the system?
That's a pretty good question. I was wondering if Bryce may have talked with the manufacturer to some degree on that. We didn't actually, we haven't uninstalled any of the fluids yet, but yeah, Bryce, I don't know if you have something you can add to that.
We did not discuss that specifically with the manufacturer, but my guess would be it could be flushed out of a system just like we would flush out, any sort of glycol solution. It's possible some of those nanoparticles could, persist in some of the far crevices of the piping way out. But if some additional water was run through there and flushed out, that wouldn't be a problem. More of the issue is the nanofluid particle, or the nanoparticles are embedded in a glycol solution, so that glycol would certainly need to be properly disposed of, and you couldn't just run it down the drain like you could by if you're draining water in a system.
Got it. Thank you. Another question that came in says, are there other commercially available products besides HYDROMX?
I'll take this one too, Joe. We are not aware of any other commercially available nanofluid heat transfer fluids that are approved by NSF at this time. There may be some others out there. I know there's competing fluids called surfactants that are also claiming similar improvements to the efficiency of HVAC systems when they're installed, and the theory behind those is they reduce the surface tension of the fluid and can speed up heat transfer. So it's a bit of a different mechanism than a nanofluid is utilizing to speed up heat transfer. So you can keep an eye out for those as well. And I forget the name of that specific product, but I know they've been making the rounds out there as well.
Sounds good. Another question that came in says, it seems like the energy recovery wheel was the only application that showed promise. Is that where rebate programs should direct their efforts on custom projects while leaving other applications alone?
That is a great question. And I'm gonna put on gonna be Bryce's opinion here right now without data to back it up. But when we're talking about thermodynamics, and I'm going to get a little engineering here, but when we're talking about moving heat around through a boiler or chiller, there needs to be energy input to move that heat. And we can't create that energy out of nowhere. So these nanofluids aren't going to reverse the second law of thermodynamics and magically create heat to be moved. What they can do is, increase the capacity of heat transfer through various coils. So that might allow like a condensing boiler to operate in a condensing mode more often, or allow a chiller system to, run with a lower approach temperature and operate a little bit more efficiently there. So in the case of that heat recovery system, which was actually more of a runaround coil system, that would have increased the capacity of those heat transfer coils, so more energy could be pulled out of that exhaust stream and transferred over to the incoming airstream in that case. So to me, that does seem like an ideal application for this system when we're not talking about energy input. We're just recovering energy from a waste stream. and recovering as much of that energy as possible, makes sense using a fluid like a nanofluid here. That's where the lab testing we suggested would make sense to pursue for, determining how can these nanofluids really affect boiler and chiller systems, and do you really need to layer in different control sequences and things like that to optimize the energy savings. We haven't, obviously we didn't, that was beyond the scope of our study here, so we didn't quite get to that level of findings, unfortunately.
Okay, thanks. Have any of these other heat transfer additives been evaluated?
If that question's in relation to the surfactants I brought up before, I've seen some case studies, but they were similar to, where we started with the nanofluids, where there were some basic, claims, but not, detailed studies with a lot of background on them that we've been able to find. Our research and evaluation department here at Michaels, when evaluating efficiency programs, has seen a number of those surfactant projects come through, and the level of detail provided has been minimal that we've seen thus far, unfortunately. So, in my mind, the jury's still out on those surfactants as well.
Okay, thanks. Do you have any tips for site selection?
Yeah, if you were to select some sites, and actually we're working with the manufacturer as a follow-up to this study to find some sites that might be good candidates for further study, and kind of along the lines of I referenced earlier with some of our other sites, the simplest sites are the best candidates. Sites that, maybe one air handler, or, relatively few systems. So you can, there's less assumptions you have to make, I guess, less potential operating sequences that can change, or, less variables, less things that can go wrong in terms of a sensor failing or anything of that nature. So, like a school with maybe one air handler or something like that would be an ideal candidate for selecting a site if you, again, wanted to do more study out in the field. But again, like Bryce referenced then in the presentation as well, I guess the simplest in terms of controlling all the different variables is to put the fluid to the test in different lab settings to, again, control variables. But I guess so sites that are as close as reasonably possible to that lab condition is what you'd want to shoot for.
Sounds good. And how long does the fluid replacement process take? Does that vary by site?
Yeah, it can. So the longer process in terms of what we observed was at that rehabilitation facility. Even though it was the loops themselves were relatively small, we were replacing it in multiple loops. So a commercial site like that took the better part of a day, with some additional follow-up for testing fluid levels and concentrations and things of that nature, whereas, as I understand it, the residential sites took more like a matter of a couple or 3 hours to be done with that installation.
Thanks. What would you say is the single most important takeaway from the results of this study?
Yeah, it's unfortunately it's not an easy answer, but the straightforward takeaway is that it's just inconclusive. At this point, there's still potential that we saw in energy savings for this technology based on some of the sites, but again, given some of the data quality issues and all the other factors that could have contributed to some of the poor results. We just can't say definitively that this is ready for prime time and ready to go with a fixed savings rate or amount for any kind of a prescriptive program. So jury's still out.
Got it. Yeah, those are important lessons learned. Yeah, I'm not seeing any other questions in the chat right now. So wondering if we should move on to the wrap up, Mary Sue?
Sure, that sounds good. Thanks. Thanks for all your questions. Thanks again for that great presentation, and thanks, Adam, for facilitating the Q&A. If you end up with follow-up questions that didn't get answered here or that you come up with afterwards, please feel free to contact one of us. The recording of this webinar and the slide set will be available, as I already mentioned, on our website in a few weeks, and the final report in a couple of months. When available, you can link to either of these from the quick links on our Applied Research and Development webpage, as indicated here on this slide. This webpage has additional resources and information related to the CARD program and to CARD research that might be of use to you, so you'd want to check it out. And the link for that is at the bottom of this slide. Thanks again for your participation today. We really appreciate your interest in CARD projects, and I do want to take a minute to mention some upcoming webinars on October 19th, next week. Canvas will present the key findings and recommendations from 2 research projects, which sought to update a couple of outdated inputs in Minnesota's current Technical Reference Manual, or TRM, which utilities use to calculate energy savings impacts and cost effectiveness of SIP measures. Then the next week after that, on the 25th of October, the Center for Sustainable Building Research at the University of Minnesota will highlight key findings from a project that investigated a novel panelized wall and roof system to enable fast and cost-effective upgrades to multifamily building envelopes in Minnesota. Then on December 7th, Ecometric will discuss the results of research they conducted into the motivations and barriers that drive the decisions of individual HVAC installers working in small to medium commercial buildings. To keep abreast of upcoming CARD projects and webinars as they are scheduled and other news related to the Conservation Improvement Program, sign up for the SIP updates through our email list. You can use the link on this slide to do that. In the meantime, please feel free to contact me if you have questions or suggestions for the CARD program or CARD webinars. And as a final reminder, there'll be a short evaluation that launches after the webinar. Please take a few minutes to fill it out and let us know how we did. Thanks again for your attention, and have a great rest of your day.